Good afternoon, good morning, good evening, everybody, my friends attending this webinar. My name is Professor Vladimir Miranda, and I salute everybody for coming to this yet another session of the INESCTEC Power and Energy webinar series. And today we have two exciting presentations. The spirit of these webinars is the following. We have usually two short presentations, short saying about 20 minutes. And the idea is that we should not put the audience to sleep. So we need to have compact messages about advancement in science and technology in our areas of power and energy, advancement either in theory, in applications, in methods, and brought to us by the relevant researchers that are involved in these actions. And today we have two topics, and I will briefly introduce to you the first speaker. Let me just share the screen to show his curriculum. So the first speaker is Professor Tarso Ferreira. He's from Brazil. And he is a researcher in INESC P&D Brazil. P&D in Portuguese means research and development. And he's a researcher at INESC P&D Brazil. And he is one of the leaders of a project about transmission line monitoring and the hardware and software development put in service in Brazil by the research team of INESC Brazil. And I'm very happy to present to you and introduce to you Tarso. And he will certainly give you news about very interesting sensors and monitoring things put live in high voltage lines. Meanwhile, we invite the participation of all the people in attending. I'm just so sorry that I believe I did not share conveniently the screen. So let me put here. Now I think you can see how he has a nice photo, and I think you can see some lines about his curriculum, so I'm saying that he's speaking from, I suppose, from Aracaju in the state of Sergipe, which is known by the wonderful beaches and seaside there, but some people may be surprised how high technology is also there, hidden in between the palm trees, etc. There is high technology there. So I suppose you'll be challenged to participate by answering or putting questions or answering a poll that will be launched in the middle of the presentation to collect some information about the feelings of the audience about the topics being spoken of. And without further ado, I will pass the screen to Professor Tarso. I suppose he has also a small video to show. So I welcome Tarso, and please go ahead. And everybody that wants to ask some question, please do not use the chat. Use the Q&A option below in your Zoom, because we will answer the questions, and if possible, we will open the microphone to participants. Feel free to put your questions or doubts or raise concerns through the Q&A, not via the chat. Thank you very much. Tarso, welcome. The floor, the screen is yours.
Okay, Professor Vladimir, thank you very much. Hello, everyone. So today we are going to have a presentation about the Tekon2 project, in which I've been one of the researchers together with several other researchers. We had about 10 Brazilian universities and NESTEC involved in the project. So is my screen okay? Can you see my shared screen?
Yes.
Yes. Okay, thank you. So, first in this first image, I'm showing a paradigm that we have in power transmission. We have, in most cases, lots of information in one side, in one substation, let's call it substation A. We also have lots of information coming from substation B. And ironically, this information travels through the power line, sometimes through OPGW cables, or even through power line carrier systems. And the power lines, they have this double job. They have to transmit the power, and they also have to transmit the data. However, if you look to the transmission lines specifically, there's not a great quantity of information coming from the transmission line itself. So it's this gray box where we try to we control by looking to the ends, to the substations. And it's in this context that the Tekon2 project enters to give us reliable information about the transmission lines, along the transmission lines. And so what can be done with the information collected along the transmission lines? Here we have some examples. Dynamic line rating is a very desirable one. The monitoring of the asset through their lives, the assets, okay, in the transmission line, fault location, condition-based maintenance. We can also have signature evaluation of transient events. We can monitor mechanical or thermal stresses. And we also have the possibility to interact with smart grid applications. And in the end, we have more efficiency, reliability, and safety in the power lines operation. Okay, so the Tekon project, it has developed a product which has the technology in fiber optical sensors for supervision, protection, and control of electro-energy systems. We have a high voltage polymeric insulator, which is shown aside. And this polymeric insulator has several fiber optical sensors. And we can measure electric current, conductor temperature, and conductor strain. And we are going to talk about the other subsystems, the signal processing unit, the solar system, which powers everything up in the tower, and the real-time monitor unit, which is our server and the substation. Next, please. So we have a change of paradigm. The main change that we have information acquired at transmission lines middle points, and the solution is embedded in the insulator. Our research teams included 9 Brazilian universities, INESC-TEC and INESC-Brasil. And the sponsor was TBE, Transmissoras Brasileiras de Energia. The project was also inside the ANEL Research and Development Program. And here we have our research line inside INESC Brazil. Next slide, please. So now we have a video to stream to you. Joanna, I would need you to stop sharing so I could share the video. And I hope that it goes okay.
You can share.
I'm getting here a window telling me that the host disabled participant screen sharing.
Please try now.
Okay, that's okay. Can you see the video?
Yeah, but no sound.
And now?
Yes.
Atualmente, as linhas de transmissão são monitoradas de forma estática, a partir das subestações e tendo como base as ideias de que o condutor está sempre em equilíbrio térmico e a capacidade de transmissão da potência é definida de forma conservadora, visando suportar o pior cenário meteorológico possível. Porém, sabe-se que a realidade muitas vezes é bem diferente. Pensando nisso, o INESC-PID Brasil, em parceria com a TBE, no âmbito do Programa de Pesquisa e Desenvolvimento da ANEL, desenvolveu um isolador polimérico com classe de isolamento de 230.000 volts, instrumentado com tecnologia sensorial em fibra ótica, o Tekon2. Além do isolador instrumentado, a solução inovadora possui um sistema computacional alimentado pelas informações transmitidas a partir da linha de transmissão. Assim, os operadores das linhas têm à sua disposição dados em tempo real, corrente elétrica, temperatura no condutor e tração na ancoragem da torre, bem como grandezas climáticas. Tudo isso de forma rápida e segura, imune às interferências eletromagnéticas, proporcionando mais agilidade na tomada de decisões e no planejamento de ações. É mais eficiência e inteligência para os sistemas de energia. É o futuro. É INESC-PID Brasil.
Okay, hope you enjoyed the video. Please, Joanna, could you share the presentation again? Thank you. So the video brought us an overview of the project. Joanna, could you please go to next slide? And here we're going to take a look in the several subsystems of the Tekon monitoring system. So let me see if I can point. Well, in the top of the image, we have several indications of the laboratory and the university in which the parts of the subsystems were developed. Here we have the OPGW cable, which is the channel through which we send the information collected in the tower to the substation. It was chosen to be this way, but it's also possible to do this using radio link, for example. In this point, we are using fiber optics through this cable. We also have in the substation the real-time condition monitoring, and there we have the data processing, visualization, we can set alarms. In the tower, we have a fiber optic distribution panel, which we connect all the optical sensors. And all this equipment needs to be powered up. So we have solar panels and the electro-optical signal processing unit, which is this red board, and we're going to take a look on it in the next slide. However, right now I'm going to say a little about the high voltage unit, which has been tested, passed through several tests, a lot of tests, in Federal University of Campina Grande, in Unifei, Federal University of Itajubá, Unicamp, Universidade de Campinas. And the insulator itself is the path through which the fiber optics going through, and the sensors are here in the lower part of the insulator. We call it the bell, to its shape. It reminds of a bell. So from the three sensors, one of them is not inside the bell, it's right here. It's a strength sensor. We're going to take a look on detail on every one of those subsystems. Please, next slide. Well, the electro-optical signal processing unit it's our brain in the field. Okay, the real-time monitoring unit is our brain in the substation. The information travels from one to the other, as I said, through the optical cable, the OPGW cable. We need to have some media conversions here, and the board also needs to supply power to the other components of the system, as the optical sources, the weather station. We also have measurement of weather conditions, and this power comes from the solar energy supply, which is on the top of the tower. Next slide. And talking specifically about the sensors, we have the first one that I'm going to approach is the current sensors. In fact, two different technologies were developed so we can measure electric current using optical, using light. We have the micro Tekon, which is based on a bulk technology. It's a crystal with high Verde constant. And we have the high Tekon, which is an all fiber sensor, and the fiber is developed to have high Verde constant as well. Next slide, please. Here we can see a test of the system, the current measurement system. We have here the signal. The photo detector has captured, and in the second graph we have the spectral behavior. Here we have 60 Hertz, which is the fundamental, of course. And both sensors are able to do this kind of detection. However, the high-bi, in theory, is able to detect faster phenomena such as surges, for example. But our other sensor, the micro Tekon, is also able to detect those surges, as we will see in the next slides. Next, please. Here we have set up on a high voltage lab. We were testing the whole system connected together. The electronics were here in this box, and the insulator is here, as you can see, the blue one. And the electronics are inside this box on a ladder besides the insulator. And when the test here was to check if the electronics were able to keep running during an impulsive current test, and it was okay. It has passed. It's kind of 6 meters, 5 or 6 meters of distance here. We had more than 60 kiloamps in the impulse. Could you please go to the next slide? And here is the result. As you can see, we have the sensor was able to detect the impulse here in the graphic in the left, and on the right, we checked the relationship between the peak value of the current pulse and the value of the current signal amplitude. So we can see we have a good correlation, and the sensor is able to detect even very fast phenomena. Next slide, please. This is the strength sensor, which is connected to a piece of hardware. It's not connected. It's not inside the insulator. It's connected to a piece of hardware, and this piece of hardware is holding the insulator cord, so we can sense the traction. And here we have a test in the lab going on. Next slide, please. Here the correlation between the measurement of the strain sensor and the applied deformation. We have a very good correlation also. Next. The temperature sensor, which is used to measure the temperature of the conductor. We also have a room temperature in the weather station, but this one I'm talking about is measuring the conductor temperature. Is a fiber grating sensor, as well as the previous sensor I've talked about, the strain sensor, and we have also a good correlation. Next slide, please. The radar station, which is we didn't develop this part, of course, and here we can see where it stays in the tower. This small guy here in the detail. Next slide. So now we're going to show some field results. The system has been in operation since August 2020. Okay, if you get this web address here, tekon2.nsbrasil.org.br, you can see what's being measured right now. So after the presentation, if you would like to check, I can share with you in the chat this address and also the video address in YouTube. Next slide, please. This photo here, we have how things got in the tower. Of course, one thing is to put everything together in the bench, the workbench, and other thing is to take them to the field. So we have in the top of the tower the solar panels. Here in the middle we have this enclosure with the optical electronics and everything. This gray box in the left side. Okay, in the right side at the top we have the strain sensor connected to the hardware piece, and in the right side down we have the insulator itself. Next slide. So those are some results comparing what has been measured in the SAGE system, which is the supervision system that TBE uses in the substation, in red, and in purple, in violet, we have the Tekon measurements, and the errors were always below 5%. Next slide. Here's another measurement during an outage. It was a programmed outage, and we have here also a very good adherence between the curves. Next. Then we have, we're going to show how to list some advantages from the Tekon2 system. We have a real-time current measurement, a redundancy in this measurement. It allows to evaluate the transmission line loading for better planning of shutdowns and expansion plans. It allows to estimate correlations between the monitored variables, which is something very rare. It's not common to have this opportunity to correlate 2 or 3 variables and check how the project is dimensioned, if it's okay or oversized. And next slide, please. It also allows to monitor current surges, temperature of the conductor, and in this case, it's possible to check for hotspots, which may shorten the conductor's life. It allows to default localization with 3 points observation, both substations and the Tekon, or if you have more than one Tekon unit in the line, you may have 4 or 5 points of observation. It also allows us to evaluate the joint consideration of all variables and calculate the dynamic limit of the transmission line in real time. Next slide. Here we have the coordination that was in XP de Brazil's coordination. We have here the partners, the universities, Brazilian universities and Inestec. Okay, and the funding was provided by TBE, Transmissoras Brasileiras de Energia, and the Brazilian Electrical Energy Agency, ANEL, within its research and development program. Next slide. Okay, that's it. Thank you for your attention. And we are here for questions.
Sorry, I'm sorry that my microphone was muted. Thank you very much, Professor Tasso. Was there any poll to be put to the audience? And meanwhile, I have 3 comments in the Q&A, and I will read them briefly. So Dr. Rui Pastana from REN, transmission system operator in Portugal, was commenting that in Portugal we tried this type of device by fiber sensing, which actually is a company that actually was born in Inestec 2 at 220 kV lines, but we had a major failure due to a fault inside the insulator because of the fiber optics inside the insulator. Would you comment, Professor Tasso? I don't know if Dr. Rui Pastana wants to comment live. Please, if you want to comment live, please give us a signal. I suppose Joanna can allow you the open microphone.
Yes, we just need to raise hands.
Yes,
okay?
please, Rui Pastana, if you are listening, please, if you raise your hand, we'll open the microphone. Meanwhile, Professor Tasso can provide some answer to these concerns.
I'm not very well informed about this major failure that happened in Portugal. I know it existed. We had a lot of tests running in these insulators, including 1,000 hours test in the lab. And we also have some changes in the media filling the insulator. We have the cable going through the insulator. However, it's not just the cable and air. The insulator is filled with silicon gill. And this silicon gel we are using has been in use in power systems since 25, 30 years ago, and it's going fine. And right now we have been online with the Tekon system running since last August, and right now, till now, we don't have problems.
Very well, thank you. Then we have a question from Professor George Lira. What were the main challenges in the project development? That is a very, very big question, because I suppose you have challenges on many fronts.
Yes, Professor George, the technical challenges were great. We have the researchers in the universities have to bring to create some new technologies as the sensing, the current sensing has several original improvements in the communications and the high voltage unit as the use of the silicon gel inside the insulator. It's a different approach. There were lots of challenges. Even the coordination challenge was great because we had 10 universities. We have lots of labs working in parallel. This project had 36 months, and for such an achievement, it's a short time. Thank you, Professor Georgi, for the question. It's a great friend.
Well, I understand that the project was done together with a transmission line operator in Brazil, and so it's the challenge should be also of coordinating research with a real-world application and with the demands of a company and with the security demands of putting a prototype in operation. And I would use the occasion also to congratulate the company for believing in new researchers, because and in a way we could say risking to operate a line with a prototype. However, the confidence was enough that the tests were guaranteeing the security, and so far 0 problems. And then we have a question from Dr. Francisco Doria Nascimento. Professor Tarso, when do you imagine that this technology will be widely applied? He says in Brazil, but I would say widely applied. When do you imagine?
Okay, these results we have shown right now have been from the Tekon2 project. We have a prototype. It's TRL7, if I'm not wrong. The technology readiness level is about 7. We are working in Tekon3, in which we are gonna have head of series, and we are trying to get to industrial production, and then it will be available for sales. And after this third part of the development, I think it will be available for the companies to buy and apply on their systems. If you need a number, I would say 3 or 4 years from now for wide application.
Yeah, well, this is an interesting answer, because there's another question actually in the chat from Dr. Almir Carlos. How about the future disponibility to higher level line transmissions? I would say that the challenge here is now a business challenge, which is asking having a partnership with industrial partners that will move this technology into the market. So it's no longer really a research challenge, although scaling up to higher voltage is always will require testing. Although let's say scaling down would be very easy I mean, to 60 kV or even to distribution levels. It's a matter of cost and etc. Scaling up requires high voltage tests, basically, because I don't think any other kind of tests are required about the electronics, the communications, the sensors, etc. That's all required is just guaranteeing that the whole set can withstand the higher voltages. And this is very exciting to see this cooperation with industry moving on. And there is a last question that I need to rush because we have the next presentation to do, but I need to rush this. Last question from Dr. Pedro Benedicto. Could you explain what in your understanding are the difference between this new device and the PMU? Or can Tekon2 be considered a more advanced version of the PMU concept? I will answer myself very quickly. It is converging to PMU concept, basically. Because with the GPS antenna and a lot of Tekon devices in the network, you will have synchronized information on many data going around in the system. So it is actually, we cannot deny, it is converging to PMU technology. And now it would be PMU concept in the middle of the transmission system, not only in the substations, but it goes beyond the PMU concept because it's not only for electrical measurements, and it provides at the substation or the control center much more data. In fact, then there is a big data problem because the information flow is coming up at a tremendous rate. So opens the way to devise new intelligent software to address diagnosis of system conditions, diagnosis of operation, diagnosis of faults, etc., etc. So I am very excited with this project. I didn't allow Professor Tarso to answer this because we need to move to the next presentation. But I would like to thank the
no problem,
the
Professor.
audience.
Thank you. Thank you for the answer.
I am enthusiastic. Everybody knows that, and this is really a great development and a great show of cooperation of Brazilian universities and the Inestec in Portugal with industry and companies in Brazil. Thank you very much, Tarso. I am going to move to the second presentation, which is in a topic that has a relation with this in a very curious way. I'm going to share the screen to present the person who is going to deliver the talk. Now I'm going to share the screen, and now I'm going to put up my. And here we have the nice picture of Dr. Mohammad Javadi, and he's a researcher at Inestec in the Center for Power and Energy, and he was before a postdoctoral fellow in the Aalborg University in Denmark and senior member of IEEE. And he has a lot of interest in several topics, including this area of flexibility. And now the connection is evident, is obvious. The previous project with the possibility of having more sensing will allow more flexibility in the operation, including more information to take some profit, take advantage from the flexibility. But there is another point of view on flexibility derived from local energy communities, and Dr. Javadi is going to share with you his point of view and his research on this. So the screen is yours, Dr. Javadi, please.
Okay. Can you see my screen?
Yes, please go ahead.
Thank you very much, and good afternoon, or even good morning for the other audience. Now I am going to talk about the flexibility provision by multi-carrier energy systems to the local energy communities. When we're talking about the energy hubs or multi-carrier energy system, This concept has been introduced from more than 10 years ago. And in this case, we have the energy hub in the main core of this system. And we have some demons rather than the classic, how can I say, the electricity. But right now we have the other kind of the demands. For example, the heat and the cooling load and heating load and the electricity. And in this case, we have the access to the natural gas as well, and also. So sorry, I want to use the pointers. Yes. And in this case, we have different resources, for example, natural gas and the electricity grid. And also we have some assets and some equipments to converting the carriers from the inside and delivering to the outside or the output of the system. In this case, we may have some storages like thermal energy storage or even electrical energy storages. So the concept of the energy carriers or multi-energy carrier system, it's talking about multiple in the input side and the output of the system. Regarding the scaling, each end user can be supposed to be an energy hub or even an end user hub. So for example, for the end user at home level, we can have a very simple hub. And in this case, we may have the other types of the energy hubs. So the residential, or commercial, and even the industrial hubs. So these figures and this slide can show us the different kinds of energy hubs with the definition of the energy vectors. And for example, for the very small industries like ceramic or plastic industries, we have different kinds of energy carriers and the consumption. So the main structure, the consumer side, can be defining as the different kinds of demands. For example, electricity, cooling, and heating system, heating demands. And we have different kinds of resources and equipments to converting the initial carriers to the preference demands. For example, for heating system, we may have some heat pumps and the combined heat and power units, the thermal units of the CHPs, and solar heating system, boilers, and the electrical heaters. And for the cooling system, we may have electrical heat pumps, electrical absorption chillers, and electric coolers. So this figure can show us the trends of the converting the different energy carriers to the demands that we may need. And regarding the modeling of the energy hubs and the flowing of energy inside the energy hubs, we have two main concepts and models for addressing the relationship between the input and the output. The first one and the simple one is comes from the classical electrical or electricity companies or electricity optimal dispatch that have been done carried in the power system, and the adding some features to the energy flows can be used for the multi-carrier energy system. And the other one is the matrix representation or matrix-oriented models. In this case, we need the algebraic equations or matrix to bridging between the input and the output of the energy hubs. And regarding the flexibility provision, generally, when we are talking about the flexibility provision in the power systems, we have different time scales and different approaches to addressing or providing the flexibility. For example, for the very short-term time slots between 4 seconds to maximum 5 minutes, we can use the AGC or automatic generation control approach and techniques to providing the flexibility without the using the humans. So this is the automatic system. And for the larger scale or large stage of the planning, for example, between 5 minutes to maximum 1 hour, we can use the rescheduling and load flow approaches. And when we're talking about very long term, we are generally talking about the new assets should be added to the system. For example, in the power system, we're talking about the generation and transmission expansion planning. And in the multi-carrier energy system, we're talking about the sizing and siting and selecting the technology, the best technology for providing the demands. And for the flexibility resources, we have different resources to providing the flexibility in the system. For example, one of the main sources of the providing the flexibility comes from the grid side. So from the grid, we have some units and some features of the grid that can provide the flexibility. Another one is the demand side flexibility using the demand response programs, and the flexibility can be provided by conventional units, very fast ramp up and ramp down units with the minimum, with very short minimum downtime or minimum uptime units. And we have some market mechanism to providing the flexibility, and we may have some other resources that can be provided through the market incentives. Another solution for providing the flexibility is the introducing the new ancillary services like the load following or frequency response or inertia response that they recently introduced in the market. And now we want to talk about the 3 main other resources. The sectoral interconnections that generally we are talking about when we are talking about the energy hubs, the transition between the resources and the carriers. So this feature can provide some resources for the flexibility provision. And the main focus of this part is focusing on the providing electrical and non-electrical energy systems. And the flexibility can be provided by the smart grids from the local energy communities, the communication system inside the smart grids. So we have one poll right now, and I want to ask Joanna to launch the poll, if it is possible, Joanna.
Yes, the poll is already launched.
Yes, we have one question, and asking, according to your previous experience, the flexibility provision needs another market, or you believe that it needs another market for the flexibility provision, or no, it can be considered as an ancillary service. We have 2 options, and if you select one of these options, your cooperation would be appreciated. Okay, so the 65% of the audience believe that it can be merged as an ancillary service. So we don't like to having another market, and they believe that we can merge these services as an ancillary service. So we can move on. So regarding the pillars of the flexibility provision in the local energy markets, we have four main pillars in this case. The first pillar is the market signals. So we will need some incentives to providing to the end users to leveraging the active participation in the flexibility provision. And when we are talking about the flexibility, we are talking about in the very short-term operation horizon. So we will need near real-time tools. So very fast tools to be incorporated in the model. And we also need the closed loop operation with the feedbacks to activating or even deactivation of the bits from the partners to providing the flexibility. And the last part of this system, it's the energy flow tools. And we are currently working on the flex energy model to modeling the behavior of the end user inside the local energy communities. So in this case, we have different carriers. For example, for the electricity, we can have the bidirectional transactions between the distribution grids, for example, in this case. And the energy can come from the natural gas companies. And inside the market, we have the day ahead and intraday markets to running the model for providing the reserve margins and the operating point of the transactions, for example. And we will need the reserve market for running in another way to providing the reserve needed by the system. And also I can show that here we have another market for the flexibility provision. And between the market and the end users, we have some aggregators to providing the energy and flexibility and the trading between the clients and the grid. And inside the local energy community, we may have different residential, commercial, and industrial hubs, and they will change the operating point of the assets, for example, boilers, CHPs, and EHP, and the other resources or consumption inside the local energy community. So for the day-ahead market, we have the one box for the forecasting. It's using the methodological data and occupation data, and also the renewable energy resources power generation by wind or solar in this case, and the forecasting system for the cooling, heating, and electricity demand. In this case, we are talking about the stochastic programming, stochastic optimization. So we need to generating and reducing the number of scenarios using the proper approaches. It can be about using multi-cardinal simulation and the other accepted tools for reducing the number of scenarios. And after that, we need to run the optimization problem with the mixed integer or linear or nonlinear optimization approaches. And the output of the day-ahead market should be or can be the operating point of the hub assets, the transactions between the hubs and the grid, the electricity grid. And the one important thing that we need to defining the state of charge of the battery or the other storage units. The typical data for the simulation or running the simulation, we need the reduced scenarios for the electricity, cooling, and heating loads for the different seasons, for example, and the tariffs for the electricity and for the natural gas that can be out from the companies providing the natural gas. So the data that we may use for the day-ahead markets is figured in this slide. And one important thing that's in this case, when we're talking about the day ahead and intraday market and flexibility provision by the very short term planning or time slots, we need to running the different simulations with different time resolutions. These figures show us the stability of the numerical results for running with the different time scales. For example, for 1 hour, 30 minutes, 50 minutes, or even 1 minute. So we know that the running time for each case would be different. So for the 1 minute, we just, when we're running the model for 1 minute resolution, it takes time, for example, 5 minutes to be run. So when we want to use this approach for 1 minute, it's not possible to adopting this approach for the model. So we need to use the simple models or moving from 1 minute to, for example, 15 or 10 minutes time resolution. And the strategy for the intraday operation, we have a different approach. Instead of the forecasting model, we will have the estimation box. And the concept for the providing the loads and the profile of generation of renewable resources is almost the same. We need the data. But in this case, we don't need the stochastic or using scenario generation or scenario reduction. We just need very simple model to being very fast running the intraday market. And in this case, when we are running the optimization problem, we will define the changes of the operating points and the transaction with the grid and also the state of charge of the devices. And the important thing is the next step. When we have some errors in the estimation or in the calculation or in the expectation of the providing of the resources, we need to run a feedback or feeding the data to the estimation box for the next time slot. So we use the model predictive control strategy in the optimization in this section. And for the estimation and the data we will need, we're using the APIs with the different structures. So we don't need we are not talking about the historical data, but we are talking about the very intensive data structure using the APIs. And for example, these two figures can show us the history and the forecast that we are feeding to the model. For the top one is about in the middle of the day, we have the history of the solar power generation and the forecasting for the other hours by 30-minute time resolution. And the below figure show us the schedule, the generation profile after 3 hours. So as you can see, the difference between the forecasting in the top figure, it's not happened in the real conditions, and the exact values are different from that data, the data and the forecasting that we have in the previous hours. So during these hours, when we're running the intraday operation, we will have different operating points, especially for the storage units, because the storage units can help us to controlling and storing or discharging the energy stored in these assets. So when we don't have any control on the renewable resources, we are moving toward to using the optimal operation of the storage units. And for the data collections, we are using the data structure from an office building for using the APIs provided by Newcastle University. And in this case, for each room in this building, we have different data. For example, we can see the cooling set point and the heating set point, and the also for the sensors that capturing the temperature inside the rooms in the different location of the rooms, the HVAC operating mode, and also the occupation data. For example, in this room, there is no guys or no researcher in the room. So we don't need to be very sensitive to providing the good situation for them. But for in the next slide, for this room that's pointed in blue, when we are collecting the data, we can see that there are some guys working in this room. So the controlling the devices, the illumination, and the quality of the air and so on should be controlled by them, or also we can use the data from this structure. In this case, we can select the data and also the set point of the devices, and also the PV power generation installed in the rooftop of the building. And when we were using the model predictive control, for each time slot, we will have different set point for the storage or the state of charge of the battery. This figure can show us I cut the one section of this figure, of this the sheet of the Excel sheet, to show you what is going on in this figure. For example, when we are running the model from the midnight, for each time 30 minutes, we will have the structure for the state of charge during 48 time slot or 24-hour for one day. After 30 minutes, the set point can be changed, even following the optimization from the previous hour in this case, or even not following the stored energy in the previous time slot. So at 0-1, we prefer to remain the exact energy stored in the battery, not charging state suggested in the previous 30 minutes. And this figure can show better, for example, when we are charging the battery during the midnight until the morning, and discharging during the daytime and until the evening. And when we're running the model, for example, from this hour until to the midnight, there is no more flexibility to changing the set point, because we put very hard constraint to remaining the exact values of energy stored in the battery, same as the initial values that we are receiving the battery from the previous day. So from this hour until the midnight, we should charge the battery to being prepared for the running the next day operation. And these two figures can show us the flow of energy for two different seasons. For example, for one working day in the winter and one working day during the summer. And as we can see in this figure, that's the electricity, the heat, and the cooling loads can be provided by different resources. For example, using the boilers for the heating, and for the CHP, we can provide the heating by these appliances. And during the summer day, we have different actions, because we will need more cooling loads. So we should be prepared for providing from the other resources. And the transactions between the electricity grid and natural gas system shows in these figures. So we can easily follow about the amount of electricity or the BTU, or for example, for the natural gas that we imported to the hub, and the energy delivered to the end users. And for the local energy community, we consider two different approaches in this case. For example, in this case, when we are talking about the integrated or independent operation, for the integrated, we may have the transactions between the inside the local energy community, between the, for example, commercial to industrial or to residential hubs. And we have some energy management systems to controlling the transaction and the needed for the next time slots in the intraday, for example, for 30 minutes. And for the independent operation, there is no solution to transacting energy between the clients of the energy hubs or the end users. And these figures, let me show you these two figures. These figures can show us the electricity, the amount of energy can be imported from the distribution grid to the community. This figure provided to show the role or the impact of demand response. For example, as we can see here, during the daytime with the high level of the electricity tariff, the consumption pattern was changed to moving from the peak hours to off-peak periods, and also here during the evening to the night or in the midnight. And the next figure shows us the energy can be bought from the electricity grid by considering the role of the energy community, and the transaction can be happened inside the energy community. So in this case, we can see also in some cases, we don't need to buying electricity outside the community. The local energy community can easily provide the energy by transactions between different clients or different hubs inside the energy community. And also the last figure shows us the role of the integrated model of operation, and also considering the demand response. As I mentioned before, the demand response can also be considered as one of the resources of the providing the flexibility. And as a last thing that I want to discuss here, we compare the results for both integrated and independent operation in the local energy community. As we know, in the independent operation, we are not allowed to selling or extra generation to the grid or to the other partners. But in the integrated, we are allowed to having some transactions between the, for example, industrial energy hubs to the residential, and vice versa for the different hours of the operation. And as we can see, the operational cost will be drastically decreased when we are using the integrated operation, using the concept of the local energy community. And thank you very much for these.
Okay, thank you. Please stop sharing your screen.
Okay, thank you.
Very well. Okay, now the microphone or the Q&A or the chat is open. for comments and so most of the comments so far are congratulations for your presentation. And must apologize to the audience for the delay we had because of technical problems. But if there is any question, please don't hesitate just to raise the hand and we'll open the microphone, or put your question in the Q&A, or even in the chat if it's possible. Arash Kamandi just wrote that thank you for your good presentation and the information you shared with us. Congratulations on the new year, and I wish you happiness and success. Well, that's a very nice message. Thank you so much. And anyway, I would just say, Professor Tasso, you can come up if you want, just to say goodbye to the audience if there are no other questions. I would just say that I would like to express my gratitude to the audience for being faithful and showing up to these webinars. Our intention is certainly not to give tutorials about the subjects, is basically to put up and share with you results from research that can be or are being applied in the power system domain, and perhaps challenge people to new ideas and perhaps new cooperation forms. So INESCTEC is open to this opportunity, and I could say also, because I'm entitled to say so, that INESC PND Brazil is also open to any form of fruitful cooperation, and we all are in communities that that are very proud in the way they cooperate with in multi-institutional projects. So here is my word of thanks. So no questions coming up. So I think I will wrap up the webinar. I'm going to thank Dr. Mohamed Jabadi and thank Dr. Tarso, and thank myself also, because the thing is, we are all speaking in English for an international audience, and the English is not our first language that we learned to speak. So please forgive us for any problems in communication, but we do our best. We use this tool. English is just a tool for us. So thank you very much, and we will announce soon our next webinar with two new topics coming up. So please pay attention. Thank you much for your cooperation, and goodbye, everybody. And keep safe, stay safe, and see you soon. Thank you, Dr. Tasso. Thank you, Joanna, for the organization.
Thank you very much.
Thank you, Mohammed.
Thank you
Goodbye,
very much.
everybody.